All right, welcome to section 3.2. Today we're going to be talking about logarithmic functions and their graphs. Our main goals in this lesson are to understand what a logarithm is and understand that it is the inverse of an exponential function. Okay, so I'm gonna demonstrate to you that it is an inverse. I'm also going to show you that I'm going to show you what a logarithm is. All right, so let's just start with that. Let's say somebody asks you what a logarithm is. You can simply respond with the fact that a logarithm is an exponent. Okay, so a logarithm is nothing more. A logarithm is an exponent. Okay, simple as that. So, but specifically, a logarithm is an inverse, or a logarithmic function is an inverse of an exponential function, right? So, a logarithm is an inverse of an exponential function. I have that written down here in this note area. So, for instance, you might remember some things about inverses back in chapter 1, one of which was that the inputs and the outputs switch places. So, for instance, if we have a basic exponential function like y equals a raised to the x power, if we wanted to find the inverse of that, we would say, well, let's make x and y switch places in that function. Okay, so we get x equals a raised to the y power. And as it turns out, that statement, x equals a raised to the y, is equivalent to saying y equals log base a of x. Okay, those two things, they are equivalent. That's why in the definition of a logarithmic function it says y equals log base a of x if and only if x equals a to the y. Okay, so it's nothing more than an exponent. And as it turns out, we can take any exponential function and rewrite it in logarithm, or rewrite it as a logarithm, and we can take any logarithm and rewrite it as an exponent because they're one and the same. All right. So when we read these logarithmic expressions, so log base a of x, what it's actually saying is saying a raised to what power equals x. Okay, so I'll kind of write that down over here. So y equals log base a of x. It's actually saying a raised to the y power equals x. Right? Give you a quick example here. Let's take a look at an exponential function such as 2 to the third equals 8. Not really a function, it's just an expression. 2 to the third equals 8. And we can actually rewrite this as a logarithm. Okay, and I'm going to write this. So notice our base is 2. So I'm going to say log base 2, right? Uh, and we're going to say log base 2 of 8, right? Equals 3. So we say 2 raised to the third power equals 8. And that's essentially what a logarithm is. So you can see the equivalency between those two statements. I'm going to do one more here. Let's do 5 squared equals 25, and I'm going to rewrite that one as a logarithm. So the base of my exponent over here on the left side is a 5. So I'm going to say log base 5. And then something's going to go here inside of the log function, and something's going to go over here on the right-hand side of the equal sign. Okay, so remember, it's 5 raised to something, and according to our exponential expression up here, it's going to be 5 raised to the second. Okay, so I'm going to put the 2 there, is going to equal some number, and that's 25, right? So that 25 is going to come here inside of the log expression. All right. So there's a couple of quick examples. We're going to explore that particular skill a little bit later in the notes, but first I want to talk about some of the common bases that we see associated with logarithms, and that is the base 10 and base e. Okay? The base 10 is referred to as the common logarithm. Right? The common logarithm, base 10. Whenever we see a log that has no base annotated, so if I'm looking at this one, it says log x, there's no base annotated. Okay, that means it's implied that it's base 10. Okay, so give you a quick example here. Let's say we wanted to evaluate log of 10,000. Okay, so we're going to evaluate log of 10,000. And the way that we're going to do this, I'm going to go ahead and use a calculator to do this. I'm going to pull up my calculator here. and just see what the calculator has to say. Put this over here. Shoot. Okay. So we'll go second quit, and let's clear our screen here. Let's do log. So the log button's over there on the left-hand side of the calculator. I'm going to say 10,000. Close parentheses and hit enter, and the calculator is telling us 4. Okay, so remember your calculator can only operate in base 10 or base E, so this log key that you see over here is simply a log base 10 button, so it's automatically going to assume a base 10. So what this means is that the log base 10 or of 10,000 equals 4. So you have to remember there's an imaginary 10 there. It's theirs. We just don't annotate it. So we're saying 10 raised to the 4th power equals 10,000. And that's definitely true. If you put 10 to the 4th into your calculator, you're going to get 10,000 back. Okay, and so that's a quick way that you can kind of check your work there. All right, the next one is the natural log. All right, the natural log uses a base E. Remember, E is just a number, so you'll see it here. And the way that we annotate a log with a base of E is by writing ln. Okay, so ln represents log E. All right. Give you a quick example here for this one too. Let's take the natural log of 95. Remember, this is the equivalent of saying log base E of 95, and we're going to evaluate that in our calculator as well. Okay, so notice right below the log button on the left hand side of your calculator over here is the natural log button, the ln button, and we're going to insert a 95 and hit enter. Okay, and what we get is 4.55387 blah blah blah. Okay, so we have the natural log of 95 equals 4.55 approximately. Okay, and again, this is the same thing as saying log base E of 95 equals 4.55. And what this exponential expression is actually telling us is that E raised to the 4.55 is about 95. So let's test that out. Let's see if that works. So E to the 4.55 equals 95. Let's see. So the E button is actually the same as the natural log button. You just have to hit second first. So you hit second ln and you'll get your E. So we're going to say E raised to the 4.55 and hit enter. And 94.63, so we get really close to 95, and that's just due to a rounding issue, but it certainly does work. Okay, so you can kind of see what those logarithmic expressions are telling you. Okay, all right. So let's go ahead and do some practice exercises real quick together to really get this skill nailed down. So you're going to see some problems like this in your book. It says evaluate each of the following by rewriting them in exponential form, or they might just ask you to take a log and rewrite it in exponential form and vice versa. And the way that I like to approach these problems, I like to think about that definition and remember that there's some number over here that we don't know what it is. Okay, since our calculators only operate in base E and base 10, we can't evaluate every log using our calculator. We have to use a little bit of know-how and really understand that definition of logarithms to evaluate certain expressions. Okay, so when we look at number 1 here, I see log base 3 of 9 equals y. Now remember from the definition that this is actually an exponential expression. A log is actually an exponent, right? So this is actually telling me that 3 raised to whatever this number y is must equal 9. Okay, so I'm going to rewrite that. So I have 3 raised to the y equals 9. And from here it should be pretty clear what y is, right? 3 raised to what power equals 9? Well, that's got to be 2, right? 3 squared equals 9, therefore y is 2. So the log base 3 of 9 equals 2. Okay. Try it again. Okay, so I'm going to do the same thing in number 2. I'm going to put a y over here. I don't know exactly what this number is yet, but I'm going to use the same approach. I'm going to rewrite the log as an exponent. So I'm going to say 5, right? 5 raised to the y equals 5, right? And then from there, once you see it in that exponential form, it should be really easy to determine what y is because 5 raised to the first power equals 5. right? So 5 to the first equals 5, therefore y is 1. So the log base 5 of 5 equals 1. Okay. All right, let's try number 3. A little bit different because we have that natural log annotation in this one. No problem. We know what the natural log of 1, ln of 1 actually means. It means log base e of 1, right? These two things are synonymous, right? So, and I can put a y in the end of that just like I have any other problem that we've done so far because that's the number that we're looking for. So we're going to say e raised to the y equals 1, right? So e raised to the y equals 1. There's our exponential form. And this one might take a minute. And once you realize what's going on here, it becomes crystal clear. But how do we get a 1 with an exponent? Well, we raise it to the 0 power, right? Anything raised to the 0 power is 1. So therefore, e to the 0 equals 1. So y must be 0. And therefore, the natural log of 1 equals 0. Okay. All right, let's try number 4 real quick. Again, I'm going to put a y over here. Now, some of these problems might require you, once you get into exponential form, it might require you to rewrite the expression with a different base. I'm going to show you what that means here. Okay, so we're going to take that same approach that we've been using. We're going to say 4 raised to the y equals 1/16. So 4, oops. So 4 raised to the y equals 1/16, right? Well, it might not be clear what exactly we are looking at here, but we do have the option of rewriting this expression a little bit so that it is more obvious. Okay, so I'm going to take a look at this 1/16 on the right-hand side, particularly this 16. It's very handy if I'm able to rewrite both sides with a base of 4. Okay, so I'm going to draw an arrow and I'm going to say, well, 4 to the y is equal, and 1/16 is the same thing as 1/4 squared. Okay. And I might remember back from Algebra 2 that 1/4 squared is the same thing as 4 raised to the negative 2 power, right? So I can rewrite this as 4 to the y equals 4 to the negative 2 power. So notice now the bases of both exponents here are the same. Okay. Therefore, I can set these exponents equal to each other. So I can say y equals negative 2. Right? Because if I put a negative 2 in for y, both sides of that expression are exactly the same, which means they must be equal. So y equals negative 2, therefore the log base 4 of 1/16 equals negative 2. Okay. All right, one more of those where we manipulate that base because those are kind of tricky. Okay, so we're going to do this log base 1/2 of 8. I'm going to put the y over there just like I always have. So my exponential expression associated with this problem is 1/2 raised to the y equals 8. Okay, and this one's really tricky because we're going to have to rewrite both sides of this expression. I want to make it so that each side of this expression has a base of 2. Okay, so let's do that. We'll kind of do it step by step. Let's focus on the right side. How can I rewrite that 8 so that it has a base of 2? All right, well, let's see. We have 1/2 raised to the y, not doing anything with the left-hand side yet, is going to equal, well, I know that 2 to the third is 8. Okay, so great, no problem. Now we've got a base of 2 on the right-hand side. How can I get a base of 2 on the left-hand side of this equation? Well, simple enough. I know that 1/2 is the same thing as 2 raised to the negative 1 power, right? So I'm going to rewrite this as 2 to the negative first. That's the same thing as 1/2 raised to the y equals 2 to the third. Okay. Now notice what we have going on here in this expression. I have this negative 1 and this y. That's a power raised to a power. And if you remember back in Algebra 2, when we take a power raised to a power, we multiply those exponents together. So I'm going to kind of come down here. So what I have now is 2 to the negative y equals 2 to the third. Now that I have the same base, just like I did in the previous problem, I can set these exponents equal to each other. So therefore, negative y equals 3, so y equals negative 3. And there's our answer. Okay, you might want to find a few of those in the book and practice those. Those do take practice because there's a little bit of intuition that goes into those problems. There I had to pick a base for each side. I picked two, and that comes from experience and doing homework and exposing yourself to those kinds of problems. So if you're not doing that, you're going to find those problems to be difficult. Okay. All right, so let's go the other direction. So before we were given a logarithm and asked to write it as an exponent, here we're going to go the other way. I'm going to give you an exponent and ask you to write it as a logarithm. All right, remember I told you that they're completely interchangeable, so I can completely rewrite these as logarithms or exponents at my will. And this is very handy when it comes time to solve exponential and logarithmic equations. Okay, so it's important that you have this skill nailed down. The first thing that I like to look for in an exponential equation if I'm trying to rewrite it as a log is the base. Okay, so you'll see here in this particular problem number 1, the base of our exponent on the left-hand side is a 4. Okay, so if I'm going to rewrite this, I'm going to say, well, the log base 4 of something equals something, right? So on the right hand side of the equal sign, I'm going to have a number that goes there, and then I'm going to have a number that goes inside of this set of parentheses. So remember what a log expression is saying. It's saying 4 raised to something, and if I look at my exponential expression, it's being raised to the third power. So the 3 is going to go over here, and 4 raised to the third equals something, which is 64. So what we get is log base 4 of 64 equals 3. So there we go. Easy as that. So identify your base, and then the other two numbers is where most students will make their mistakes as to which number goes where. So just remember what that log expression is trying to tell you. Okay, so here we go. So here we've got a base of 10, right? So this is our base. We have a base of 10. So I'm going to have log base 10 of something equals something, right? So this 10 is being raised to the negative second power. And so we have 10 raised to the negative second equals 1 over 100. All right. And remember, since we want to use proper annotation, whenever we see a log base 10, we don't normally write the 10 there because it's a common log. Anything base 10 is common log. So this is actually just the log of 1 over 100 equals negative 2. We do not need to annotate the 10. All right. Let's try number 3 real quick. This one uses that base e, right? Because we're going to see that base e come up. So our base here is e, right? So we're going to have log base e. Clean that up a little bit there. Okay. And we're going to have the log base e of something equals something. Here e is being raised to the second, so the 2 is going to go over here, and e raised to the second equals 7.389. And since this is a log base e, we should use proper annotation. So log base e is the same thing as writing ln of 7.389, and that is going to equal 2. Okay, so let's test that out. So this is saying e squared equals 7.389. Let's see if we've got this right. So if that's true, then the natural log of 7.389 should equal 2. So I'm going to hit natural log of 7.389 and see what the calculator has to say about it. And we get 1.99999, and that's really, really close to 2, so there's a little bit of a rounding issue there, but not a big deal. It certainly works, so we know that we did it right. So if you're working with those problems in base 10 or base E for right now, you can at least use your calculator to check your work and make sure that you're doing it correctly. Okay? All right. So let's do a couple quick exercises here. We're just gonna run through this. It says use your calculator to evaluate each of the following. Make sure you round to 4 decimal places here. Instructions are very specific. So we're just gonna go ahead. We've got log of 25. So we have log 25, and I'm gonna hit enter here. We get 1.3979. So 1.3979. Easy, right? We just want to make sure that you can use your calculator to evaluate some common logarithms here. Okay, let's try natural log of 37. So we're going to hit natural log button over here on the left of 37 and hit enter. And we get 3.6109. So 3.6109. And, Mr. Weldon made a typo here. We do not need to do number 3 again. It is the same problem. So we'll just kind of skip over to number 4 here. So let's do the natural log of 1/2. Okay, so 1 divided by 2 is the way that we're going to put that in there. Okay, and hit enter. And we get negative 0.6931. So negative 0.6931. And let's try number 5. Okay, so number 5, we have the natural log of negative 3. So I'm going to hit natural log. I'm going to hit negative 3, close parentheses, and enter. And we get an error. Well, it says use the calculator, so we got an error. You should probably start thinking about why are we getting an error here? What is wrong with negative 3 that the calculator can't evaluate this natural log? It seems easy enough. But for right now, I'm just going to go ahead and put an error here because, I mean, the calculator won't do it. We'll talk about why in just a minute. Let's try number 6 here, log of 0. That shouldn't be a problem, right? Well, let's see. Let's see. Log of 0. Okay, hit enter, and again we get an error. I wonder why. So we get an error, and let me explain to you why we get errors on number 5 and number 6. Okay, and this is always important to pay attention to when we talk about any kind of function. It's important to keep in mind the domain and the range of the function that you are dealing with. Okay, so recall back in section 3.1, if we had a function f of x equals a to the x, right, a basic exponential function, we found that the domain of that function was all real numbers, right? We can put anything we wanted into it, right? So we can put anything we want in for x, but what we can get out was a little bit restricted. We could not get anything out that was negative or 0, right? So it was up to, but not including 0, up to infinity, right? So any positive real number. Well, now we're looking at a function that is a logarithmic function. It's an inverse of the exponential function, right? So f of x now equals log base a of x. And in this case, since it is an inverse, the domain and the range are going to switch places. So therefore, our domain is now going to be from 0 to positive infinity, not including 0. And our range is going to be anything, any real number. We can get anything out of a logarithm, but we cannot put in any negative numbers or 0. And that's why we got errors on 5 and 6. Okay. So I'm just going to put a recall here, right? Because we needed to recall that f of x equals a to the x stuff from a previous section. All right, so I'm going to demonstrate that these are actually inverses of each other. If you recall back in chapter 1, we said that two functions are inverses of each other if there is a reflection about the line y equals x, right? So we're going to graph these two functions, and I'm going to show you that f of x and g of x are reflections of each other over the line y equals x, right? So remember, y equals x, I'm going to put this in red, is this line that kind of runs diagonally across the coordinate plane. It doesn't have to be an exact sketch, but you might want to go ahead and start by drawing that line y equals x. Don't worry about being too accurate with it. You'll see once you get both of these functions graphed that it's clearly a reflection. Okay, so the first function that we're dealing with here, f of x, is f of x equals 3 to the x. So I'm going to start by making a table and getting some points that I can plot on this graph. Okay, so I have x and I have f of x, and we are dealing with our function here, f of x equals 3 raised to the x power. Okay, so I'm going to pick some values for x to work with here. Let's pick some simple values like 0, 1, 2, and how about -1? Okay, so those are some good values to pick. And what we're going to do to get some ordered pairs to plot here is I'm going to plug those values for x in to f of x and see what I get out. And I'll put those into the table. So if I put a 0 in for x, we get 3 raised to the 0 power.
Mr. Flessner, if you're still in the building, call Mary Newton's phone. 6116.
Sorry about that. So we're going to plug in 0. 3 raised to the 0 power is 1. Okay. So we get a 1 there for 0. If I plug in a 1, right, we get 3 to the first power. That's just going to be 3. So I'm going to put a 3 here. 3 squared is 9, so we get a 9. And 3 to the negative first is 1/3. Okay, so let's go ahead and plot those points and see what we've got going on. So at 0, I'm at 1. Right, so we're about right here. And then at 1, we're at 3. We're about right here. And then at 2, we're at 9. So there's that one. And then at negative 1, we're at 1/3. So about right here, right, getting close to that line. We already know what this is going to kind of look like. It's got a vertical or a horizontal asymptote at y equals 0, and then it starts to curve up, demonstrating exponential growth. Okay, so there's f of x. Right. So now I'm going to go ahead, I'm going to start focusing on g of x, right? So g of x, according to the problem here, is log base 3 of x, right? Which is the inverse of 3 to the x. I'm going to come down here and I'm going to say, well, we have x and we have g of x. Create a table and get some ordered pairs that I can plot on the graph. And let's take a look at this g of x real quick before we start doing this. So g of x is log base 3 of x, right? So if we think of that g of x as being a y, which we can do, we can say that it's the same thing as saying y equals log base 3 of x. And remember that this is actually an exponential. We can say 3 raised to the y equals x, right? So 3 raised to the y equals x. So these two things here are equivalent statements. All right, and I like this form better for creating a table because it shows that rather than picking x values, it would be easier to pick y values to create my ordered pairs. Okay, so I'm going to pick some y values. Let's pick the same y values that we picked for x values in the previous function. Okay, so I'm going to say 0, 1, 2, and negative 1. And notice I picked the same numbers that I did in the previous problem, except I put them in the g of x column rather than the x column. Because if I look at that exponential form, my x's and my y's have switched places. All right, so here we go. If I put a 0 in for y, I get 1. If I put a 1 in for y, I get 3. If I put a 2 in for y, I get 9. And if I put a negative 1 in for y, I get 1/3. Okay, so now I have 4 ordered pairs for g of x. I'm going to come back up here and I'm going to start plotting those points. Try and keep everything here on the same screen. We'll plot this one in red. So at x equals 1, we're at 0. So there's a point right there. At x equals 3, we're at 1. So we're going to be about right here. So I got my second point. Then at x equals 9, we're at 2. So there's 2. And then at x equals 1/3, we're at negative 1. So about right here. And as it turns out, it looks like there is a vertical asymptote at x equals 0. And this one kind of curves up. And it looks, if we look at these graphs, you can clearly see that there is a reflection about that line y equals x, right? So here's y equals x, here is g of x, and there is f of x, and it clearly demonstrates that reflection about the line, which shows that they are inverses of each other. And if you look at those graphs and you think about the domains that we're dealing with in a basic exponential function, our domain is negative infinity to infinity. And our range, if you look at that graph, is any y value that we can get is going to be a positive real number. In other words, it can't be 0. So we're going to say up to, but not including 0. But it does go up forever towards positive infinity. And then when you take a look at g of x, and we start thinking about the domain and ranges of g of x, when we look at the domain, it looks like our x values can't be anything less than 0. In fact, it never actually gets to 0 because of that vertical asymptote. So we're going to say up to, but not including 0, but it can go off towards infinity along the x-axis. Okay, and then our range, it looks like we can obtain any value of y that we want. So we can go from negative infinity to infinity. And just to verify this graph, I want to go ahead and do it on the calculator as well. So I'm going to go to the calculator. I'm going to hit this, clear out anything that you have in there already. And let's just do some basic ones here. Let's do um, let's do this one. Let's, instead of doing log base 3, because remember our calculators only operate in base 10 or only operate in base 10 or base e. So we're going to say our first one we'll say is 10 to the x is our first function, and then we'll do the log of x, right? So that's log base 10 of x. So those are actually inverses of each other, and when we take a look at the graph of these two, there you go. And I'm just going to move that window over. Let's do a window of negative 5 to 10 perhaps, and then let's hit graph and see if we get a better viewing window for that one. Yeah, it's a little bit better. And just so that we can make sure that we see that reflection over the line y equals x, I'm going to come over here to y3, and I'm just going to hit x, right? So this is the same thing as saying y equals x. So it's going to draw that line y equals x in for me, and I'm going to hit graph, and there you go. You can kind of see that line splitting those two functions and creating that reflection. Okay. All right. Well, that concludes this lesson. See you next time.